Since I've started my research in computer science, which is approximately 35 years ago, I've been interested in mainly a few issues, all of which can be characterized within theoretical computer science. Most of them, or practically all of them, lie within three main general areas. One I would call discrete mathematics, the second one distributed computing, and the third one networking. Within the area of discrete mathematics, I've did a lot of work since the beginning and actually until now on issues concerning combinatorics and graph theory. Since the mid-1980s, I have conducted research on distributed computing, in which I was involved in getting positive results like design and analysis of algorithms, and negative results, design or actually proving lower bounds and impossibility results. Later, since the late 1990s, I would say, I've been conducting research in various areas of networking, in which I take model of networks, usually ATM networks, and then optical networks, and investigating all kind of algorithmic issues regarding them. I would say that most of my research have been involved in models that are related to graph theory, and mainly algorithmic part of it. And at the end of this initial presentation, I think I would like to mention that I was lucky to collaborate with many excellent researchers all over the world, which of course are co-authored on many of my, or in most of my papers, as well as my PhD and master students back home at the Technion. This is, I would say, a difficult question to ask someone who is doing theoretical research in computer science. I must say that this is like, in one interview, one of the Russian leaders, I think it was Gorbachev, a journalist wanted to ask him, what can you say about the Russian economy in one word? You know, the journalist, of course, was expecting a short answer, so Gorbachev said, in one word, good. So the journalist was not, of course, happy with the result, with the answer, and he asked him, okay, how would you describe in 2 words the Russian economy? So he said, not good. So in this less humoristic approach, when you do research on theoretical issues, it's very difficult to judge the applicability of your results. But let me try to give some answer which I believe covers most of the things that I've been doing. Most of the problems I've been working on, especially the ones that stemmed from distributed computing and then later networking, came from real applications. And then when you start to work on the problem, you only see the problem as a very vague, unclear set of ideas, which you have to clarify. Most of the time, we clarify them in terms of, we model them in terms of graph theory, and then we understand exactly what question we are asking and what answers we can come by. And then, step by step, you try to identify what is the complexity of the problem, and to design the algorithm to prove results about how difficult it is to solve the problem. For example, I was lucky to join the area of distributed computing, as I said, in the mid-1980s, and this area just started to become a research area about 5 years earlier. So I was lucky to take part in studies that deal with fundamental problems of that research issue. For example, one of the main issues was leader election, and the question was, how can you identify a processor in the network? So I took part in many studies which gave a specific answer to the problem, which, for example, showed you can solve the problem in this and this complexity, but also in terms of lower bounds, meaning that you cannot solve the problem more than so and so. So this kind of results of lower bounds, and I've been involved in many works that have to do with lower bounds, this kind of results show you that no matter how clever you are, you cannot solve the problem better than something, better than some value, some threshold of your resource, time, number of messages, whatever resource you have in mind. Then, for example, in the area of networking, which I'm doing for the last 20 years or so, one of the main questions is you have a problem, you have many parameters. You have to build a model for the problem and to try to understand its complexity. Here I can give one example of applicability. For example, we have been doing a lot of research in the algorithmic side, which has to do with online algorithm. In online algorithms, you don't get all the input in the beginning, but the input comes on time, and you have to solve the problem very well, even though you don't know what input is going to come. And the comparison you do is with how an optimal algorithm will do it if it knew all the information beforehand. So for example, and of course without getting into technical details, we showed that in one scenario, if you want to optimize some switching cost in an optical network, and the input comes online, that is along the way of the running of the algorithm, then we design an algorithm that can solve the algorithm, can solve the problem with no more than 75% with no more than 75% of the resources used by an optimal solution. Now you can ask, okay, 75% is not so good. Yes, but we show that no matter how clever we are, no one can solve better, because we can show a scenario where no matter how clever you are, you will need to use this 75% of the optimum. So some of these investigations and studies of online algorithms are very applicable, because many, I would even dare to say most of the scenarios in networking where you have to satisfy users or satisfy requests of users are online problems. And if you know how to design an algorithm and how to, of course, give a very good performance algorithm and shows that you cannot do better, this is a very, very applicable kind of result. Here at UC3M, I'm not associated with any specific project, but I think I am bringing my expertise on algorithmic studies, and so far it has proved very helpful, and let me explain it in a few minutes. When most of the problems that you do with networking can eventually be modeled as a problem in graph theory. Then the first question is to model the problem. The second question is, okay, now I have a clear definition of the problem. Do I have a good algorithm for this? In computer science, we usually distinct between an algorithm that can be solved in polynomial, which runs in polynomial time, or an algorithm which is cannot probably run in polynomial time. The technical term here is NP-hard. Now, the first question is to ask, can you give me a polynomial time algorithm, or can you show that the problem belongs to these NP-hard problems? The second thing, once you have this characterization, what do you do? Because practically most problems, I would say 99% of the real problems belong to the hard problem, to the NP-hard problems, and then you have to ask, okay, what can I do? So first thing is to solve the problem in specific scenarios, which is okay. But the more challenging problem is to say, okay, you cannot solve the problem optimally in polynomial time. So if I give you only polynomial time, how much can you get closer to the optimum? And here you have to use a lot of machinery that we have been developing in algorithmic studies to design approximation algorithms and to analyze them. And the last thing is, of course, to go to the online scenarios where, regardless of whether the problem is easy or difficult, you don't have all the input in time, and you have to solve the problem, so you have to compete with the optimal solution which knows all the information beforehand. Now, so far I've been involved in 4 or 5 projects here in UC3M, which most of the problems all the problems come from optical networks and wireless networks. So in some of them I helped even to define the exact problem, how to make the model in graph theory. Then in some of them I managed to show, okay, you have a problem, we modeled it, now I showed it, it's difficult to solve, or it's NP-complete, NP-hard, as I mentioned before. And third, in some cases, I said, okay, let's say how difficult or how easy it is to approximate the problem, and I also made some steps and some contributions in this respect. So I would summarize and say that I bring my expertise in graph algorithms in all the algorithmic areas. Algorithmics is the short for the theory of algorithms. And starting And this expertise helps in solving problems and making research in problems from the very first step of modeling the problem as a problem in graph theory, then identifying whether it's easy, can be run in polynomial time or not, and second, once it cannot, help to solve the problem in special cases and help in the analysis of approximation.